Hello and welcome to the channel. We are continuing our integration series, and today we have a definite integral. Well, this problem is similar to what we had in problem 14 of this sequence, so it will be a nice exercise for you to go back to that question, perhaps after solving this one, and try to do it on your own. It was a indefinite integral of x times e to the square root of x dx. So it will be a nice exercise which will involve one more or two more steps than what we'll do today, and in this way you can sharpen your technique on integration. Now, there is a playlist which contains all of the videos on this topic. It's in the description down below. I'll also put additionally the link for 14th video of this sequence. Now let's try to evaluate this integral. Well, as most of you already guessed, we'll use substitution because we see square roots of x complexify our integration. So it's better to make some substitution. In fact, I think in 14th video I explained in details why do we need substitution here and why can't we work with just e to the power square root of x as it is. Alright, so our substitution is pretty trivial. It's y is equal to square root of x, and what I'll do the next is not that trivial, I'd say, because I prefer writing it as y squared is equal to x, and in this way I can write dx is equal to 2 times y dy. We just differentiated. Of course, it was not a necessity. For those of you who are wondering why did we just square this and then evaluated dx, we could go in this way, like the second pass. We just differentiate both sides again. It's dy is equal to derivative of square root of x 1 over 2 times square root of x dx. Alright, and after we got this, we know that square root of x is actually y, so we have 1 over 2 times y dx. In this case, we have dy times 2 times y is equal to dx, the same equality that we found earlier, but with a couple of more steps. So I prefer squaring this and getting an answer in a more simple way. Okay, now we can go on and write. Well, first we need to calculate boundaries. We almost forgot about them. Let's write. Now, since y is equal to square root of x, so if we have x is equal to 4, then y is equal to 2, and if x is 0, then y is 0. Well, now we can proceed, since we have everything in our hands, including our dx. Therefore, our integral converts to an integral from 0 to 2 of, well, square root of x is y, so y times e to the square root of x, like e to the y, and dx is 2 times y dy. We multiply this by 2 times y dy. Here we are. Now, since 2 is a constant, we can write this out of an integral. It will be 2 times integral from 0 to 2 of y squared times e to the y dy. Great, now we have what we wanted. We have e to the y and y squared. Just for the note that e to the square root of x is a composite function, and we try to avoid it because it's hard to find an antiderivative of such functions, whereas for simple ones as e to the y, it's quite straightforward. I think I've explained in details why we cannot apply integration by parts here with e to the square root of x, like why finding its antiderivative is not obvious. And now that we have e to the y, we know that its derivative and antiderivative is just e to the y, so nothing to worry about. And as for y squared, we can just differentiate it multiple times and get 1 eventually. Like differentiating it over and over, basically 2 times, we'll get an integral of e to the y with some terms, and this over here is just e to the y. So we will be done with our problem. Now, without saying too much of words, let's dive into the problem and apply integration by parts. Now here, of course, we will use differentiation for the polynomial function to reduce its degree, and just integration, or just finding an antiderivative for the exponential function. Now, for the first time of applying it, I'll use notation of u and dv. Those of you who are watching my videos constantly, they already know that I'm not tend to use this u and dv notation because it takes time and space. I rather prefer writing it in our minds, and it's somehow more efficient and actually easier for me personally. Now we have u is equal to y squared, then du is 2 times y dy. Now dv we took as e to the y dy. Basically its antiderivative will be just e to the y. Alright, and we want to have obtain the form of u times v minus v times du. So what we have here is 2 times, I'm opening up the brackets, first uv, it's y squared times e to the y, and don't forget the limits or boundaries, minus an integral of v times du, e to the y times du, it's 2 times y dy, and this is a definite integral as well from 0 to 2. So what we have in our hands currently is 2 times, let's compute this over here, it's 4 times e to the 2, like 4 times e squared, and for 0 it's 0. So to make it short, it's just 8 times e to the e squared. So straightforwardly we just write 8 times e squared minus 2 times an integral of, well, now please note that here we also have 2, and we can write this before the integral sign. So it's basically 4 times an integral, right? So it's 4 times an integral from 0 to 2 of, y times e to the y dy. Great, now we have the similar structure like polynomial times exponential function, except this time the degree of polynomial is 1 unit smaller than what we had before. And now we'll apply integration by parts one more time to reduce this to 1, and then hopefully we'll find an answer after integrating just e to the y. Now, as I said earlier, I prefer not using du and dv notation. Not that I'm doing something special here, just trying to do this in our minds. We choose two functions. Well, first let me write 8 times e squared. So, and 4 times, opening up the brackets, we choose two functions. First, the function will differentiate, and the function that we'll need to find an antiderivative of. For this particular case, we want y to be the function that will differentiate, and e to the y dy is the function that we need to find an antiderivative of. First, we just find an antiderivative. An antiderivative for e to the y is just e to the y. Now in the first step, we just rewrite our initial function, which is y, multiply this by a function that we found, an antiderivative of this, which is e to the y, minus, well, in our case we have boundaries, minus an integral of, we just rewrite what we just found, it was e to the y, and then we differentiate our function that we didn't touch earlier on. It's y, and its derivative will be just 1 times dy. I'm just writing dy. I hope this was clear, but don't hesitate writing some questions in the comment section below. In early videos I was talking about this. Perhaps I'll make a new video on integration by parts where I include this as well. Now, as for our final answer, we have 8 times e squared minus, here we have 2 times e squared and minus 0, so it's just 2 times e squared, and Multiplying this by 4 gives us minus 8 times e squared. Then we have plus 4 times an integral of, well, sorry, here I forgot to write boundaries. An integral from 0 to 2. Well, if you initially have definite integral, you just need to keep in mind that in each step you will deal with boundaries. So whenever you see an indefinite one in your integration or computation, just ask yourself a question whether it should be like this or not. And losing the track of what I was doing, I accidentally just rewrote the integral sign here, whereas I just needed to compute its integral and write its answer in a final form. Okay, we have plus 4 times, well, its integral is just e to the y with boundaries from 0 to 2. Now we have our final answer. It's naturally 0 plus 4 times. Now for this expression we have e squared minus e to the 0 is 1. So basically it's 4 times e squared minus 4. It's our final answer. This time not using AI to rectangle it. Alright, here's a brief overview of what was done. As I mentioned earlier, after seeing this video you can go to 14th one. I'll put the link in the description and try to solve this on your own. There I believe you will have one more step somewhere here, like you will start with y cube as far as I remember and deal with that. Just don't forget to add some constant in the end, since that will be an indefinite integral. If you have some further questions, feel free to write them in the comment section below and reach out. See you in the next videos. Bye.